Cool. Yeah, this is how I record the lessons, but I'm trying to do something different, like I said. So you see how there's now a little speaker? So that way you guys can actually just listen to the audio for each slide, but you need to download the PowerPoint to do that. I figured that might be a little bit better than having a whole video. Yeah. Cool. So, and I'm hoping that this will be less laggy than the document camera app. All right. So propanal and propanon. The thing I want you guys to remember about these two is that they are structural isomers of each other. So they have the same formula. So I'm going to draw both of these molecules out so you guys can see them and see that they have the same number of carbon, hydrogens, and oxygens. So propanal, prop 1, 2, 3. Al tells me aldehyde, double bonded oxygen. And then my last step is always to put in the hydrogen. Remember, everybody should have 4 bonds. So this carbon on the end has 3 hydrogens. This one only has 2. This one will only have 1. So that is what propanal should look like. Propanon, very, very similar. 3 carbons, 1, 2, 3. In this case, the carbonyl, that double bonded oxygen, is going in the center. And then what I need to do is fill in the hydrogens. So 3 hydrogens on the end, no hydrogens on this carbon here because it's already got the full 4 bonds. And last one's over here. That looks like it's floating a little bit. It is 1 molecule. I might draw a little line just to indicate that, like, it is still 1 molecule. I just should have put my carbons closer. Yeah. Are we okay with that so far? All right. So when we are thinking about similarities between these two, both of these are examples of structural isomers, which we talked about last topic. So structural isomers are things that have the same formula. Same formula, same number of carbons, same number of hydrogens, same number of oxygens, or whatever it is. All that's different is that they're arranged in a different bonding pattern. So if I was to check the atomic mass of both of these substances, let me grab my calculator. So with that same structural formula, it would be C3H6O. They all have that. If I want to translate that into the mass of that molecule, I have 3 times 12, because mass of carbon is 12. Can you guys see that in the calculator? Is that better? See the calculator? Carbon is 1, and I have 6 of those, and then oxygen is 16, and we only have 1 of those. So the total mass for this formula is 58. So that's, again, something that's going to be similar about these 2 molecules. The reason why I point out the mass is because we're going to use that in the mass spec, which is our last spectra. Yeah, so I did 12 times 3, 1 times 6, and then 16 times 1. So that is the atomic mass of the atoms, is how I got those numbers. Cool? All right. What's something else that we know will be similar looking at the spectra that we just talked about, IR? Same peak. So they both will have carbonyl. In IR. So we know that's about 1700. So these 2 molecules are very, very similar. Do you agree? So it's going to be a challenge then to figure out which one's which. If we were doing organic chemistry, we would do something like Toland's test, use one of the oxidants, use Benedict's test. Those would all be ways to distinguish the 2, but we're in spec now, so we're going to use a machine. All right, can I move it? Okay. So let's look at IR spectra, and we don't know if this IR spectra is for the propanal or the propanon. But they both would have similar IR spectra because we're looking for that peak here at about 1700, that carbonyl peak. We also see up here that I've included the formula, and the formula is the same. So what we then do is we move on to the CMMR data, and the CMMR data will look different. So propanal, it's just this, real simple to look at, and we're just counting the peaks. 1, 2, 3. So that's what propanal looks like. Propanon, 1, 2. Now shall I explain why? Why is 1, 2, and why is 1, 3? All right. What we're looking for is unique carbon environment. So we're thinking about, does the carbon have, like, what does the carbon have attached to it, and is it repeated? We're looking for symmetry. And I think Hannah's already figured out what we're talking about. So I'll do propanon first because that one had the symmetry. If you notice, this is one of my carbon environments. It's a carbon. It has a C double bond O, and it has a CH3 and a CH3 attached to it. So I'm just listing out the things that it has attached. These two carbons here have exactly the same list. So these are the same carbon environment. So carbon environment number 2, when I look at it, has 3 hydrogens, a C double bond O, and then a CH3. And if I looked at this carbon here, it has the exact same makeup. Oh, let me move the exact same makeup. 3 hydrogens, it's right next to the carbon with the carbonyl that has a methyl at the end. So that's why this one only has 2 peaks. So 2 peaks, 2 environments, that's what you'll see on the CMMR. For the propanal, in this case, it has 3 carbon environments. So this is my first carbon environment. It has the carbonyl, a hydrogen, and an ethyl. This is my second carbon environment. It has 2 hydrogens, the aldehyde ending, and a methyl. And then this one has the 3 hydrogens, a CH2, and then the carbonyl bit. So that's 3. So this one would have 3 peaks on the CMMR. So what you are looking for is symmetry in the molecule. So CMMR is useful. It can give you an idea of how many carbons are there. So in this case, it told me there's 3 carbons, and that matches. In this case, it told me there was 2 carbons, but if I just did a 2-carbon molecule, the mass wouldn't match the mass spec. So what that tells me is that there's got to be symmetry in the molecule, and one of these are counted twice. Do you guys want another example of me drawing a molecule and showing you what it looks like? Okay. Let me grab another piece of paper. I'm happy to do a couple just so you guys can kind of see it. But counting these carbon environments is basically what you need to do when you're thinking about your various isomers. So, let me do CH3, CH2, CH2, CH3. Just an alkane. Yeah. How many carbon environments would I see on a CMMR? Hannah says 2. Anybody else? All right, the answer is 2. So these 2 have the same carbon environment, and these 2 have the same carbon environment. The thing to keep in mind is that sometimes things can be tricky, and you have to kind of watch out for them. So like, for example, let me actually do I'm just going to draw a couple molecules that are isomers of each other just so you can see the difference, because I find seeing lots of examples helps. And so all of these are examples of structural isomers, correct? Yeah. Because they all have the same formula. All right. So if I'm looking at this first one here, this one has 3 environments because there's symmetry in the molecule. So this one gets labeled as 1. Those 2 are 2. and the N ones are 3. Because when you write out the list of what they have would be exactly the same for the N carbons. So I'd expect 3 peaks for this one.
Does it matter where the peaks are?
Yeah, it does. And that's what we're going to talk about in our next lesson. Because the next lesson will then be able for us to use to back up IR. It'll also be able to use to figure out, which isomer potentially. And then you use the mass spec to help verify. All right, this one here, how many peaks? It's not 3. So these two are not being counted as the same. Because this one's right next door to the alcohol, and this one, it has a carbon in between that and the alcohol. So they're not the same list. Does that make sense? Or do you want me to pull it out more?
I'm confused.
Okay. So it's all about what's on the list. So when I'm looking at this guy, that's 1. That one's 2, that one's 3, that one's 4, and that one's 5. They're all different. There's no repeats. Which one are you guys thinking are the same?
The 2 and the 2.
You think these two are the same? All right, so number 3, if I was listing out what number 3 has, it has 2 hydrogens. It has a CHOH, CH3, and then it has a CH2CH3. That's what carbon number 3 has. Carbon number 4 has 2 hydrogens again. It has CH2CH3, and then the alcohol's over there, and it has a CH3 attached to it. You see how they're different? So the thing that's different about these two is that this is 2 carbons and the alcohol. This is 3 carbons and the alcohol's in the middle. This one is an ethyl. This one is just a methyl. So carbon 3 and carbon 4 don't have the same things attached to it. Whereas when I looked at the first example up here, because there's symmetry in that molecule, this carbon and this carbon both have the same list of, that's 3 carbons with the alcohol right next to that, 2 hydrogens, and a methyl.
Okay, yeah.
And then these ones on the end have the exact same list. It has this full list, and it's 1, 2. If I cover it from going this direction, 1, 2. And then the alcohol, and then 3 hydrogens.
So the last one will also not be...
The last one is also the same. It's going to be 5.
Yeah. Okay, yeah.
So it's a common misconception. It's a common mistake that people go, oh, CH2, CH2, CH2. These all 3 must be in the same environment. They're not, because they're different distances away from the alcohol, which makes them different molecules. Or sorry, different environments. Huh? Yeah, so you need some sort of symmetry. You need some sort of branching pattern. So if I have, for example, CH3, CH3, CH3. Let's say I have this as my alcohol, and that's another variation. Is it? No, too many carbons. Too few carbons, actually. All right, so if I'm looking at this molecule here, and I'm trying to figure out its carbon environments, this carbon in the center is obviously different. So with this carbon in the center, it has the 3 methyls and the OH. That's obviously 1 carbon environment. These 3 branches are all the same. Because it has, when you cover it, that has a carbon with the alcohol and 2 branches coming off of it. It has the 3 hydrogens. Cover that up, same list. Cover that up, same list. So these are all the second environment. So this would only have 2 peaks. That's symmetry, yes. Yeah. So basically any form of symmetry we get is part of the is going to be double counted. And so that's why when we looked at the CMMR data, propanal has 3 peaks because it's not symmetrical. Propanon has symmetry, so it only has 2 peaks. And that's how the CMMR data can help us distinguish between those 2 isotopes, because everything else about those isotopes will be the same. Same mass spec, sorry, not same mass spec, same mass, same IR. Cool? All right. So the key takeaway about this is that if there's any symmetry in my molecule, there's going to be less peaks, because the symmetrical peaks will be counted as one environment. Are we good so far? All right, shall we practice it? You guys saw the answer to the first one. All right, I'll stop this recording and we'll go back to the PowerPoint.